So, lesson 5, the final lesson of this unit. This used to be the last lesson of the year, but I'm doing some equilibrium at the end of this yet. So, here's our picture. This is a transformer. What is a transformer? Well, I'm going to muck this diagram up a lot. Don't write this down. I'm going to be circling and labeling. There's two solenoids. See them? One there and one there. With different numbers of turns of wires. That's key. We generally call one of the solenoids the source, either the primary, and one of them the secondary solenoid. Give me a moment. I got a student coming in late. Continue. So we have the primary and the secondary. We have an input voltage. We'll call that either EMF primary or V primary. We have an input current. We have a number of turns of wire. We have a secondary turns of wire. So let's walk through this. The input side is called the primary. Output is called the secondary. That's pretty easy to remember. It works as follows. The alternating current, can all of you underline the word alternating? The reason it has to be an alternating source current is you have to have a changing flux. If you just have a direct current, you will have a magnetic field induced, but the magnetic field won't be changing, and so you won't be able to induce a current in the secondary. You need a changing flux. That's a classic trick question, by the way, Emily, hint, hint, on your test. There's a good chance you may get a picture of several transformers, and one will be hooked up to DC, direct current. That one won't work. So the alternating current produces a sine wave current. What we do then, don't write this down, I'm going to gum up this diagram, is in this solenoid, we have current going this way, then this way, then this way, then this way. And what that does is that creates an oscillating magnetic field, a magnetic field going this way, then a magnetic field going this way, then this way, then this way. And what you get is a changing flux through that secondary coil. Oh, and because you've got a changing flux through this secondary coil, you're going to induce a current and induce a voltage. The changing current produces a changing magnetic field in the primary coils. The iron yoke, we usually have a laminated iron core, that acts to trap the magnetic field and it conducts it through the secondary coils. It really amplifies the changing flux because the iron itself also becomes magnetic. The changing magnetic field passing through the secondary coils creates an induced voltage in the secondary coils, a different voltage. What this allows us to do, Alejandro, is input, and I'm making up numbers, let's say 80 volts and output 160 volts. Or input 10 volts and output 50 volts. And it's a very easy, nice, mathematical, linear relationship. It works as follows. Oh, example 1. Would a transformer work with a direct current? Only if you flick the switch on and off, faking an alternating current, essentially by hand. In fact, you would only get a transformer working the split second you opened the switch, because that's when the changing flux occurs. Oh, as soon as it reached constant flux, though, you know more. And the split second you close the switch, you get a brief pulse of current, no more. But basically, will it work with a direct current? Because you don't have a change in flux, you have to simulate a change in flux. Flicking it off and on, sure, would work. Otherwise, nope. No, unless you faked it by flipping a switch on and off rapidly. By the way, that's essentially, I'm dumbing it down, that's what the alternator in a car does, because the source current in a car is a battery, which is direct current. An alternator changes that into an alternating current, and now you can use that for, well, for sparks, for starters, for the spark plugs, because that works better, but also for, you can now change the voltage. We find transformers in our homes since most of our household appliances don't work with 110 volts of alternating current that BC Hydro supplies us with. Computers, radios, TVs, they all have transformers within their cases. the black adapters that we plug into items, those are transformers. I'm looking for mine on my computer right here. This contains a transformer. Probably a step-down transformer, because I don't think this thing needs 110 volts, pretty sure. How do you know? Because it can also run off the battery that's inside of this thing, and I don't think there's any way that that battery is putting out 110 volts. Okay. Those little barrel-shaped, gray-shaped things that you see on telephone poles, those are transformers. Have you ever wondered what those are? They're every few houses, and what they're doing is they're stepping down the voltage going through the power lines to the 110 volts that your house wants. Or the boxes that you see, the BC Hydro boxes in some neighborhoods, those are transformers as well. Okay. So they're seen on power poles or green metallic enclosures at ground level. BC Hydro uses them to step down from the thousands of volts they use to transmit electricity to the 110 volts they supply your home. By the way, it's technically, I think it's 113.4. Usually we'll round off and we'll call it 110 or 120 because those are nicer numbers to work with. In fact, usually 120 because that means you have a 60 hertz alternating current, which gives, that's how those ticker tape timers that you used in Science 10 and Physics 11 kind of work. Turn the page. Here is the transformer equation. This is the mathematical relationships between transformers. It turns out, Graydon, can you hand me your formula sheet? I want to get the right thing on top because I do it from memory, but I might not have the right variable on top. What do they want? Well, secondary on top. Okay. The ratio between your secondary voltage and your primary voltage is equal to the ratio between the number of turns of wire in the secondary solenoid and the number of turns of wire in the primary solenoid. Okay. Oh, but also it's related to the current in each, but the current in each is backwards. Secondaries on the bottom, primaries on the top. Okay? There's 3 equations. We only go, Rob, 2 at a time. And it's a cross-multiply equation. Okay? What this does, Sebastian, is this gives us really complete control. Hey, you need a voltage of 18.34. I can do that. Just it's all about the number of coils of wires on my primary and on my secondary. Oh, you need a current of whatever. I can do that. Oh, but the only way I can give you a bigger current, it's going to be a smaller voltage. Sorry. Or you want a smaller current? I can do that. It's going to be a bigger voltage. It's easier to use like this. Example 2. If we want to step up to set voltage up from the 12 volt in our car battery to the 11,000 volts used by a spark plug, and our induction coil has 100 turns in the primary, how many would there be in the secondary? What are they asking us to find? I think the number of coils, number of turns. What are they giving us? Source voltage and secondary, primary voltage and secondary voltage. So my equation is going to look like this. Voltage secondary over voltage primary equals number of turns of wire secondary over number of turns of wire primary. I don't care about current. They didn't talk about it. What's the secondary voltage that we want in this circuit? What's the source voltage? Car battery is a 12 volt. Equals. Well, they told us that our induction coil has 100 turns of wire. So if you're building this in the factory, how many turns of wire had you better put around your secondary coil? And yeah, the nice thing is it's straight grade 8 cross multiplying. This is about as nice an equation as we can end the year with. It's certainly simpler than a lot. How many turns of wire will there be right there? I think it's going to be 100 times 11,000 divided by 12, right? Good gosh, Dueck. 91,700. Turns. How big was my primary voltage? What was my secondary voltage? Is our secondary voltage bigger or smaller than our original? Bigger. We call this a step-up transformer. If the voltage is smaller, do you know what we call it? Step down. And it's based on voltage, not on current, because a step-up transformer gives you a bigger voltage, smaller current. Oh, and by the way, if they had told us the current information, we would find actually there's a smaller current on the right-hand side, on the secondary side, than there was on the original, because the voltage got bigger. That's why in this equation, S on top, oh, P on top for current, S on the bottom. And I made a little note here, a car battery is direct current, but an ingenious circuit called an alternator regularly interrupts the flow of current, which produces a changing flux, enabling us to transform the voltage. Note, I wrote here, transformers that increase voltage are called step up. Transformers that decrease voltage are called step down. You'll need to know that terminology because I'll use it in questions and you'll have to clue in, oh, if it's a step up and he's given me two voltages, the first voltage must be the primary, the smaller one, and the second voltage, the bigger voltage must be the secondary. He didn't necessarily tell me which one they went with, but step up means I'm getting a bigger voltage. Okay. An ideal transformer, the reason we say the word ideal transformer is you actually do lose a little bit to heat. In fact, those big barrels that you see on the telephone poles, much of that infrastructure is designed to deal with keeping it cool in such a way that you maximize your efficiency. But the basic structure is still like this. So an ideal transformer has 160 turns of wire in the primary, 800 turns of wire in the secondary. The primary circuit is connected to 120 volts AC. It is alternating current, so this will work. What is the EMF across the secondary winding? And is this a step up or a step down transformer? What do they want us to find? Sorry? Can you read the sentence that says what is? You missed the key word each because you said primary twice. Okay, so what are they asking me to find? And what's EMF another word for? Sorry? Louder, come on, mister. Have some authority. Voltage, because they need to hear. Yeah, voltage. Okay? So they're asking us to find secondary voltage. What have they given us? Turns. Okay, so my equation is going to look like this. By the way, I just know for voltage and turns, same letters on top. In other words, I could go like this. I could put primary on top, but it's going to be primary on top over secondary on the bottom. It's going to be secondary on the bottom. Or you can put secondary. I think on your formula sheet, secondary is on top. Whatever. It's straight cross multiplying. N over N equals V over V. Let's fill in what we know. The primary, how many turns of wire in the primary, Brett? Okay. How many turns of wire in the secondary? What's the primary voltage? 120. Secondary voltage is what they're asking us to find. Hey, again, Shashan, straight cross multiply and divide. This one, I don't even bother getting the VS by itself. I plug in the numbers because I've done cross multiplying since like grade 7, right? What am I going to type in my calculator? What times what divided by what? What am I going to type in my calculator? What times what divided by what? Sorry, louder, I can't hear you.
120 times 800 divided by.
Good, do it. What do you get? 600 volts? Nathaniel, what was our source voltage? Our primary, I keep saying source. What was our primary voltage? What was our secondary voltage? Step up or step down? Step up. It's a step up transformer. example 4 says, find the unknown. By the way, the circuit symbol for a transformer is, there you go. There's a gap in the circuit, and we do a little curly half solenoid, a little curly half solenoid. We're saying, hey, it's two solenoids separated by a gap because we're inducing. There are no electrons traveling from here to here. What we're doing is we're using a changing flux to induce a current over on this right-hand side. It says, find the unknown current and voltages, and then label the transformer as step up and step down. Okay, they're giving me, if you look somewhere in this circuit, they have to give me two pieces of information. They either have to give me both voltages, both number of turns, or both currents. Which should they give me in this circuit? Number of turns, that's going to be my starting point. So I'm going to say N primary over N secondary equals V primary over V secondary. Now the key for current show is it's going to be N primary over N secondary. Current is reversed. Current is going to be secondary on top, primary on the letters don't match going across. Go look at the equation and that's what you'll notice. Have I got room? Yeah, I can cross multiply right below here, I think. Let's even do that. Number of turns in the primary. 30 over number of turns in the secondary, 120. Voltage in the primary, they told me, 120. So I guess I'm trying to find the secondary voltage. What times what divided by what? In fact, I'd go 120 squared because I'm lazy, divided by 30, which is what? Mr. Dueck, you're not typing the numbers in. We actually have to type these in ourselves. What did you get, Kevin? 40? 480? Primary, 30. Secondary, 120. Ooh, careful, current is flipped. And this is the most common mistake. Kids match up, they line up the current. No, current is reciprocally related. Secondary current, I don't know. That's what they're asking me to find. Primary current is what? 2? What times what divided by what? Oh, I can do this in my head. It's going to be 2 times 30, 60 divided by 120, 0.5 amps, yeah? Step up or step down transformer? Sebastian. But wait a minute, the secondary current is smaller. Because the up and down is defined in terms of voltage, not in terms of current. So let's even make a little note here. Step up transformer. Believe it or not, this question has been a 7-mark question on the provincial exam. 3 lines and cross multiplying. So you know what? This will be a written question on your test. It's not close to free marks, but be careful how you plug things in because the most common mistakes, again, kids get the currents. They do it wrong. Let's try another one.
So for like velocity and the number of coils.
Not velocity.
Or voltage.
By the way, now you're starting to see why maybe that EMF symbol isn't such a bad idea after all, or maybe we need like 50 letters in our English alphabet. No, we'll use Greek. Go ahead.
So we can put primary or secondary on the top as long as the current switch.
So if you put primary on top, for coils, primary is on top. For current, primary is on the bottom. Yep.
But you can switch it around.
Yep. Because when you flip both sides of a fraction, yeah. And in fact, I have a habit of doing primary on top because that's just what I look for first, and that's how I write it. But I noticed that's why I grabbed Graydon's formula sheet. I said, I think they put secondary on top in the formula sheet, and that's fine too. Okay. Hey, try B and C and D on your own, this whole page. I'll do them up here, look up every so often. Let's see if we all get the same thing. First step is to figure out what they gave you 2 of. That's going to be your attacking point. Is that right? 5,000? Yeah. Great, and you're supposed to try this on your own without looking up the whole time and copying it down. Just saying. Oh, they didn't ask me to find the current here, Dueck. Sheesh, that was a waste of time. Read the question. Oh, they did ask me to find it here. Okay. What'd they tell me both? Oh, the nut coils again. $120 times 5. 600 divided by 60? 10? Careful, Dueck. Primary goes on the bottom. 600 divided by 5. Well, 600 divided by 10 would be 60 divided by 120. I got 1,000 volts for B, yes? For C, I got 10 volts and 120 amps. D, I haven't done yet. I have a feeling D, I might need to use a calculator. Oh, and again, they've told me both, so the number of coils. Primary over secondary equals primary over secondary. Ooh. Primary over secondary equals secondary over primary. 5 over 75 equals, okay, they told me the secondary. What's my source current? And for D, do you get 18,000 volts and 1.5 amps? Okay. How can we try and trick you? On the multiple choice, there's a good chance I may give you several pictures, one of which is direct current. Don't pick that one. So I may just say, which of the following is a step-up transformer? One will have one will be the correct one. One will be a step-down transformer. I'll give you some numbers, and I won't. You have to kind of calculate it and think about it. One will be a direct current, and I don't know. Another one will be maybe the same number of coils of wires in both, which means it's neither step up nor step down. Doesn't do anything. But think about what we're able to do here, Joe, without actually connecting the circuit to the other side of the circuit, because no electrons are traveling across this. We are able to send a current from one section to another. Transformers, nice devices, very nice, all based on Faraday's concept of changing flux, inducing a current. There's a reason why we kind of think him as the father of electricity. All of our infrastructure is based on his ideas. Next page. So, Austin, the fact that we can change the current and the voltage to whatever we want, very, very useful, because this is what determines why and how we ship power across the country. So transformers, I wrote, are essential to long-distance transmission of electricity. And an example will illustrate why it's more economical to deliver electrical power at high voltage than it is at low voltage. A generator at City A delivers power at a rate of 1 megawatt to City B. Mega is 10 to the 6th. Is that what it is on your formula sheet? You got the chart of all the prefixes there somewhere? Yeah? Okay, so 1,000,000 watts. The total resistance of the very low resistance cables between A and B is only 10 ohms. So our power lines, we make them very low resistance. Okay? We can ship this power two ways. We can ship it at a low voltage. We can ship it at a high voltage. If we ship it at a low voltage, well, first of all, the current, because power is VI, the current that I would need to do that, if I want to ship 1,000,000 watts at 5,000 volts, I have to have 200 amps going through these wires. How much power would I lose going through those wires? Well, the power loss as heat is going to be, now, where do I lose that power? I lose that power, Nathaniel, due to the resistance in the power lines, because I'm heating up the power lines. So for me to calculate the power loss, I'm not going to use V times I. I want to use an equation that takes into account the resistance of the power lines. So I'm going to use I squared R, which was the other version of Joule's law that we came up with when you plug in V equals I times R. And you end up with losing 4 times 10 to the 5th watts of power as heat. Of 1,000,000 watts supplied, you lose 400,000 watts. You're basically heating up the air. 40% loss. So we don't ship power at 5,000 volts, Alejandro. We don't ship power at low voltage. Instead, what we do is, using transformers, we step up the voltage as high as possible. We step it up to maybe 500,000 volts in situation 2. The current would be power divided by voltage. The current would be now only 2 amps. The power loss, which is I squared R, would be only 4 watts out of 1,000,000. Now, instead of losing 40%, you're losing not 1%, not 1/10 of 1%, 4 1,000ths of 1%. You're almost completely efficient. This is the basis of our entire nationwide power structure. We ship power across the country, Graydon, at high voltage, high efficiency, because if we shipped it at low voltage, all we'd be doing was, you'd see the wires glowing red hot. It'd be dumb. Okay? Let's try an example. Example 5. Let's walk through this. Suppose the Dueck Hydroelectric Company decides to ship, so we have 150,000 watts of power that we've stored that we want to sell to Ontario. We're going to ship it through 2 ohm transmission lines, and I'm going to ship it at 20,000 volts. How much power is lost? Well, first I need to figure out what current I need to ship this at. By the way, this is a nice written question. I like this question. I need to figure out what current I need to ship this at. Power equals V over I. How much power am I shipping? 150,000 watts. What's the voltage I'm shipping it at? 20,000. If I want to do this, what current will be flowing through those power lines? Can someone crunch the numbers for me, please? Is it 7.5? Yeah? Is that okay, folks? Am I losing you? Dylan, you with me?
Yeah.
Get rid of that. Dumb software update. 100. Oh, add a 0. Sorry, I'm missing a 0. Thank you, guys. It's 150,000 watts. Put a 0 there. Is it 7.5? Okay. 7.5 amps. How much power would I lose? I don't want to use V times I. I need to somehow take into account the resistance of the wires. I know the current in the wires is 7.5. I know the resistance of the wires is 2 ohms. So I'm going to use this version of Joule's law. I squared R. It's going to be 7.5 squared times 2. How many watts do I lose? What do you get? 58.5? Is that right? I don't think so. 112.5? I think you forgot to multiply by 2. 112.5 watts lost. What's the efficiency? Well, efficiency is how much I put in, 150,000 on the bottom. How much was I able to keep? What did I lose? 112.5. What did I start with? 150,000. So I kept 149,887.5, and I'll multiply that by 100%. How efficient is this? It's pretty good. This is one of the times when we could get close to 100%. We can't get 100% efficiency. We can get stinking close. What do you get? You really want to just keep your calculator out and start typing some things. Yes, my front row little buddies here. Divided by 150,000. You get 99.9% efficient? Like I said, we can get pretty close. What if I do this same thing, Gianluca, 150,000 watts of power, I'll fix the typo later, 2 ohm resistance power lines, but I'm going to ship it at a much lower voltage. Instead of 20,000 volts, 560 volts. First thing I need to do is figure out the current. How? Well, I know power, I know voltage, power divided by voltage, because power was defined as VI. Nice review of some of our circuitry stuff. It's going to be 150,000 divided by 560. How? 268 amps. How much power will I lose then? Well, the power loss is going to be I squared R. It's going to be 268 squared times 2. This number squared times 2. And I get a power loss of 14,395. What's my efficiency? Well, I started with 150,000. I lost that much, so if I go 150,000 minus what I lost, I'm left with 6,505 times 100% to make it a percent. 6,505 divided by times 100. Yeah, 4.3% efficient. That power savings is why it is definitely worth it for us. Again, I don't know if you've wondered, why have we built this huge nationwide infrastructure with power lines going over rivers, over mountains, in the middle of nowhere? Why are we doing that? Because by shipping power at that high voltage, I'm telling you, even though it costs money to maintain all those wires, we watched that video a couple of months ago of the helicopters coming in and fixing the wires out in the middle of nowhere. Even though we have to do all of that, hey, still totally worth it. Totally worth it. 99.9% efficient. Finish the course? Well, no, we're going to be doing a little bit of equilibrium. Finish the material that you'll be seeing on your final exam. Finish the material that you will be assessed on. Little comic there, the elaborate cheating scam, getting a skywriter to come and write the physics formulas in the sky for them on their test day. What's your homework? Ultimate magnetic induction review. Alejandro, you can now do every single question on that ultimate magnetic induction review. I have covered every single topic. I have covered every single detail and every single nuance. Okay. I think I have a little